start tonight with a challenge. Here we have a video of a public pool teeming with children. We're going to play about 15 seconds of the clip and see if you can identify the child in the video that is drowning. Raise your hand if you were able to identify the drowning child. All right, that's pretty good. It's about 10% of the audience. So for those of you that didn't see, here's the kid highlighted in red, and also the lifeguard safely swimming over to save the child. Now let's do one other quick challenge. We have a 12-hour-long video from a traffic camera in Colorado. We're going to play the video at 1,024 times speed and see if you can identify any patterns in how cars or pedestrians move across the intersection. Okay, now raise your hand if you notice anything in particular in that great clip. Any patterns? Anybody? Okay, so about 0%. So the pattern we were actually looking for here was is shown in these two clips here. So we pulled these two clips from the video we just showed you. And in both of them, if you look to the left side of the frame, you'll see the town sheriff pulling over to the side of the street at night, getting out of his car and dancing in front of the traffic camera because he knows it's there. This clip actually appeared 4 separate times in the video that we just showed you.
The purpose of these examples was to highlight two abilities, if you will, that the human brain and body aren't great at. First is the ability to focus on multiple things at once. As illustrated by the swimming pool example, we really aren't built to see and understand multiple things happening in the scene at one time. If any of you have ever done the Harvard Challenge, where you watch a group of people practicing basketball, you know how easy it can be to miss even painfully obvious things. This is called selective attention, and it's the process our brains use to filter out the barrage of sensory information that they receive every second. Selective attention also comes up in witness testimony, where you have two witnesses swearing on their life that they saw completely different things. The second ability is the ability to perform a task indefinitely, without any drop in performance. We got a taste of this with the 24-hour video from Jackson Hole. The reality is, we simply can't do the same thing 24 hours a day, 365 days a year. As much as some of us would like to be non-stop productivity machines, we have to eat, we have to hydrate, we can really only operate for 16 hours a day before having to completely shut down for another 8. If we really wanted to watch the whole video, we would have to watch it at a ridiculously fast speed, which means we would miss the important things we were trying to understand.
Despite our not having these two abilities, we think that these two things are the key to solving a set of safety and efficiency problems with the spaces that we use every single day. For example, we've managed to build absolutely incredible highway and city systems, yet in the US we still spend 47 billion hours a year waiting in line in these cities and on these highways. We have retail stores that stock every product we could ever possibly need, yet when we go to these stores, we still have to ask for an employee to get our size jeans from the back, or spend 10 minutes wandering around the store trying to find the item we're interested in. And despite the proliferation of workplace safety protocols and employee safety training, we still in the US experience 13 workplace-related deaths every single day. To solve these problems, we need to measure and analyze our behavior in these spaces indefinitely and continuously. By measuring how many millions of cars and pedestrians move throughout downtown Manhattan, we can identify global patterns of behavior that help us to optimize streetlights, streets, and sidewalks, all to minimize congestion. If we can analyze behavior on a factory floor, we can provide real-time alerts to workers who miss a step in a safety protocol, preventing them from entering a potentially dangerous scenario. To accomplish all of this, we can use cameras and computer vision to analyze our behavior in these spaces without pause and without any drop in performance over time. These devices can operate indefinitely, focus on as many items as we need them to, and with recent advances in computer vision, are getting closer and closer to recognizing not just objects, but actions and behaviors. So this brings up a really important question. How exactly does a computer see an image or a video? And why is it such a difficult problem getting a computer to understand that image or that video? To illustrate the complexity of the problem, let's look at an image from a computer's perspective. So, can anyone tell what this is? If we remove the background, it gets slightly easier to see. And if we look at the actual image, we see that it's a puppy. So, unfortunately, computers are not blessed with our absolutely incredible vision processing system. So where we see a puppy, they just see a whole bunch of digits. So the fundamental challenge in computer vision then is teaching a computer to recognize that this set of digits is a puppy and that set of digits is a person, and so on, until they can understand people, places, and actions exactly as we are able to.
In the last 10 years, deep learning has emerged as a promising new approach to computer vision. Deep learning is a branch of machine learning that uses artificial neural networks to analyze patterns and data. At their core, artificial neural networks are algorithms that model our human brains. Our brains consist of hundreds of billions of neurons, each of which is connected to many other neurons. And a neuron's basic function is to take in a set of inputs, add them up, and fire, or activate, if the sum of those inputs is greater than a certain value. We attempt to recreate this phenomenon in artificial neural networks, but on a much smaller scale, using only millions of interconnected digital neural units. These neural units also take in inputs and create a weighted sum and activate if that sum is greater than some value. But in order to be able to use these networks to do the task they were designed to do, we have to train them. And before we train the networks, they really resemble the brain of a human child, moments after birth. Much like a human child, these networks have to see and understand examples from the real world in order to be able to detect objects. In order to be able to detect these objects, we have to show the network millions of images. For example, we might have to show the network millions of images of dogs before it's able to recognize dogs. Recently in computer vision, the next focus for researchers has been detecting over 1,000 different types of objects and images. For example, researchers from Microsoft recently released a network that could draw and label over 1,000 different types of objects. Here we can see that the network was able to detect a person and a dog, but also more peculiar things like an umbrella and a motorcycle. But this image, this single instant in time, is not enough to truly understand human behavior. To do that, we have to be able to look at a sequence of images and say that, for example, this sequence of frames is someone doing gymnastics. Researchers from Stanford have recently released a network that is actually able to watch video and understand what happens. Here it watched YouTube videos and was able to say what sport it was. For example, here the sport was basketball.
In the retail industry, marketers' entire job revolves around understanding as much as they possibly can about their target customer. Their average age, their gender, what they eat, where they shop, all to ensure that their marketing campaigns resonate as much as possible. With cameras that understood human behavior, we could help marketers understand their customers at an even deeper level by actually analyzing their behavior in store. This would have the consumer benefit of making stores that are both easier to shop and also better at stocking items that customers actually care about. Between 1990 and 2003, in the US, there were almost 6,000 cases of wrong site, wrong procedure, or wrong patient operations. In the future, we could place a camera above an operating table to actually provide real-time warnings to a surgeon when they begin operating on the wrong patient or the wrong area of the body. And this system could be preloaded with standard details about the surgery: site, patient, procedure, surgical materials list, allowing us to go even deeper, alerting a surgeon when they leave a foreign object inside a body, or warning an anesthesiologist when they provide an insufficient or incorrect dosage. Continuing in the healthcare space, we could help reduce the spread of viral infection in hospitals. The number one method or mechanism by which viral infection spreads in hospitals is healthcare professionals failing to wash their hands between patients. With the camera system in hospitals, we could provide a simple alert when a doctor or a nurse forgets to wash their patient or wash their hands after finishing with a patient, potentially reducing the spread of infection to their next patient. This could reduce the 1 in 25 people that get a viral infection after staying in a hospital.
And this technology doesn't only apply to life or death scenarios. Has anyone ever taken an exam in a large lecture hall and seen other students cheating? If so, you know how frustrating that is after having studied a week for that exam. When I was at Purdue, most of my exams consisted of over 100 students, a few TAs, and a professor, making it effectively impossible for the professor and the TAs to catch instances of cheating. But with just 4 cameras in this auditorium, we could watch every seat in the house and instantly report suspicious behavior down to the front of the room. The professor could then look at that video and make a determination about how to proceed. In fact, watching large groups of people is incredibly important, like we saw in the beginning. Every day in the US, 10 people die from incidents of unintentional drowning. Parents and lifeguards have to watch every person in the pool and look for that split-second moment when their head goes underwater. With a deep learning system that understands human behavior, we could assist parents and lifeguards and act as a backup set of eyes for monitoring pools and beaches. These are just a sample of the problems that we think can be solved with a computer vision system that understands human behavior. This is where we realistically see the future of artificial intelligence, as a tool to help people, not replace them. This is the future we are working to build. Thank you.